Hi everyone, welcome back to Math 261. This is Scott. Let's get started. So we're going to follow up on the last section with now section 3.2. The last section was really about how to find the determinant, like what the actual process of cofactor expansion was. And now, in this section, what we're going to discuss is what the determinant determines. It's called the determinant, which means it must determine something. And let's try to figure out what that is. So this is properties of determinants. Well, when we started this class, we kicked things off by a discussion of row operations and row reduction. Now, nothing in this class really gets us very far away from that fundamental understanding. So everything that we learn, we should ask ourselves, does this relate in some way to row operations? And in the case of determinants, it does. So let's discuss row operations and determinants. Now we're going to be stating a lot of facts here that are provable. I mean, they wouldn't be mathematical facts if there was no proof for them. However, this is not an upper division linear algebra class. This is an introduction to linear algebra, so we'll be omitting most of the proofs and arguments that would support a lot of these things, and instead we'll just more or less announce facts that you can then, if you wish, investigate the proofs of them by going down an internet rabbit hole. But here's what we're going to state. So first off, our setup, we have a square matrix A. Again, just like with invertibility, we don't even care about the very concept of determinant if what we're talking about is not a square matrix. So A is n by n. So in other words, square. All right. So let's discuss our row operation, friends. And we'll make a little two-column thing. So the row operations and then their effect. On determinants. So we have three main categories of row operations, and let's just try to figure out what each one does to the determinant. So the first major category of row operation is that we can scale, say, one row of a matrix by a factor. So scaling. And let's say scaling a row by a factor of k, just so we have a letter. So the effect of this on the determinant is that it will multiply the determinant by, you guessed it, k. Multiplied by k. Okay. So there's that. Secondly, let's say we interchange two rows. Well, if you interchange two rows, this has the effect of making the determinant the opposite. So the determinant is multiplied by -1. And those of you who are more familiar with vectors will recognize that this is also what happens in the cross product. If you interchange the order of the two factors of the cross product, the result will be negative. Negative, whatever the first one was. And then thirdly, the classic add a multiple of one row to another. Now this one has the most surprising effect on the determinant. You might think, oh, okay, well, probably I would have to multiply it by whatever that factor was, etc., etc. But nope, the most surprising thing of all happens, nothing. So the determinant is unaffected. The determinant is unaffected by this. Now, the most interesting thing as far as our purposes are concerned, the most interesting thing about these three categories of effect is that none of these will turn a determinant that was not already zero to zero. Multiplying, so not changing it at all, obviously, but multiplying it by -1 also won't change a non-zero determinant to zero. And furthermore, here, if the determinant is multiplied by a non-zero scalar like k, that will never turn a non-zero determinant to a zero determinant. So note, none of these operations would turn a non-zero determinant into a zero determinant, and vice versa. So if the determinant was not already zero, legitimate row operations will not cause it to be. And for that, I should point out, of course, scaling is always by a non-zero factor. So what does that mean? Well, let's think about that. So row reducing produces RREF. And if when you RREF something and it reduces down to make the identity, that is actually the exact process we would go through to find an inverse. But since the identity has a determinant of 1, determinant of 1, that means that we can only row reduce down to the identity if the matrix has a determinant that's not 0. So if and only if the determinant is non-zero. Now that is a part of the invertible matrix theorem. So therefore, we can add to the theorem with this. So theorem. This is the invertible matrix theorem, volume 3. A is invertible if and only if determinant of A is not equal to 0. However, being invertible was only part A of the invertible matrix theorem. Everything else that was part of that theorem then also depends on the same property of the determinant. So, along with this, we can use the determinant to find out all kinds of things. For example, such things as whether the columns of a matrix are linearly independent or not. So we can find out that's one thing. 2. Whether a collection of n vectors span Rn. 3. Whether there are non-trivial elements of the null space. 4. Whether the matrix equation has a unique solution. 5. So the matrix equation, the standard one, AX equals B, has a unique solution. And so on, etc. But these are some of the most important properties that come up in practice. In particular, in Math 256, so those of you who are going into that after this, these are all properties that we will end up using determinants to determine. We will be doing them more in the world of functions than of vectors in Rn, but the principle is the same. We'll make determinants, and in particular, the main kinds that we'll be making are what are called the Wronskian determinant, and that will help tell us if a collection of functions are linearly independent from each other. And then there is the Jacobian determinant, which has applications for systems of linear equations or also just vector calculus as well. And that and the determinant of that will be an important feature for whether a certain kind of transformation is invertible, whether a certain category of linear differential equations has a solution, and how you would change an integral if you were to do a transformation of the variables. But that's all outside really the scope of this class. That's a matter for Math 256. But that's part of what makes determinants so important. All right, and one more note. What we just said before about the row operations and what they do for finding the determinant, that is actually what your calculator does when it calculates the determinant. Is it actually row reduces the matrix, and it uses the effect that each row operation has on the determinant until it gets down to our REF form. So note, computers and calculators, things like that. So computers use row reduction. Use a row reduction technique. Rather than cofactor expansion. To calculate determinants, and the reason is because it's much more efficient. So those of you who have dabbled in the dark arts of computer science may know what it means for to discuss the order of an algorithm, but in particular the computational complexity of row reduction is on the order of n cubed over 3, which is polynomial time, versus cofactor expansion, which is on the order of n factorial. So for example, if we were doing a 25 by 25 matrix, that would be way beyond the capacity of a human being to do, unless it was, upper triangular or something like that. But a computer can do it in a matter of seconds, because it does, or actually a fraction of a second, because it does it with row reduction. But if it were to do it by cofactor expansion, and it were doing, I believe the figure is if it did a trillion operations per second, it would still take 500,000 years to compute that determinant. So this is just a side note. So it's order of n cubed over 3 versus the order of n factorial. So this is only for those who are deep in the weeds of computer science, but it's just a fact. Just a fact that is of some interest. For us, though, our needs are going to be mostly capped at the 4x4 matrix for doing things by hand, and in the matrices will typically be pretty rich in zeros, so the operations won't be too cumbersome. So we can use cofactor expansion rather than learning some new technique. And in particular, for a 2x2 matrix or a 3x3 matrix, cofactor expansion is just fine. Okay, now let's try some examples. Let's try some examples of some of the things that determinants can help us determine. So example. Use a determinant. To answer the following. Alright, first off, I'm just going to give us a matrix and we're going to ask, is this matrix invertible? So, the matrix A is going to be 3x3, column 1 will be 5, 1, 0, column 2 will be 1, negative 3, 5, and column 3 will be negative 1, negative 2, and 3. So, the question is A invertible? Alright. Well, it says use a determinant, so we have to find the determinant. So let's get calculating. So cofactor expansion will be our technique here. So the matrix 5, 1, 0, 1, negative 3, 5, negative 1, negative 2, 3. Now we can have our pick of which column or row we wish to expand along, and I'm gonna say I like the look of maybe row 3. Now the checkerboard, plus, minus, 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 and plus, minus, plus. That will be our indication of the signs of the cofactors. Now, what this is going to be then is going to be 0 times whatever it is, doesn't matter to us, and then minus, because the checkerboard says so. So it's going to be 5 times, and now what we do is we take the entries of the submatrix that we get by deleting column 2. So it's going to be 5, 1, negative 1, negative 2, and then plus 3 times, and now the submatrix is 5, 1, 1, negative 3. Alright, so what have we got here? We've got negative 5 times negative 2 is negative 10, minus negative 1, so that's plus 1. So notice I'm cutting out some of the steps that I wrote before when we were just getting our feet wet, because we're getting a little bit more experienced here, so I don't want to bog us down in a forest of arithmetic. Sometimes showing more steps actually opens up the opportunity to make more mistakes, rather than the other way around. So then what do we have here? Negative 15 minus 1. And then does the crisscrossing calculation. And here we have negative 9 times negative 5 is positive 45. And here we have, I guess it's going to be a negative, so it's going to be negative 16 times 3, which is 48. And so that equals negative 3, which importantly for us is not equal to 0. That's the most important thing about it. And so the answer is yes, A is invertible. And it's invertible because the determinant of A is not equal to 0. So that's the kind of question you can answer by means of a determinant. So I know that it is invertible even without actually finding the inverse itself. Now there is actually technically, we'll mention it, but we won't really make use of this very often because it's computationally very inefficient. But there is actually a formula where once you calculate the determinant, you can actually cut straight to the inverse. But that's not it's not a very often used formula because it is not very computationally efficient. Okay. So that's one kind of question we can answer. Another kind of question would be, I could give you a collection of vectors, and I could ask you, are they linearly independent? So, is the set, and the set, let's say, is going to consist of vectors, so they're going to be three entry, 4, 6, 2, and then negative 6, 0, negative 6. And then negative 3, negative 5, negative 2. So is this set linearly independent? Well, these could be the columns of a matrix, and then we can find the determinant of the matrix. So I'll just make a matrix out of them right now. 4, 6, 2. -6, 0, -6, -3, -5, -2. And we can expand however we want. Let's go with second column. And the checkerboard here is going to go plus, minus, plus, and really all we care about is the second column. Whichever one you're expanding along is the only one that really matters for the checkerboard, but for the sake of completeness, we'll fill in the rest of it. Okay, so we're going to have -6, so it's going to be +6 times. Now we make the submatrix, so what is called the minor. So 6, -5, 2, -2. So it was -6. There, I'll write that in the first step, just so the paper trails there and nobody gets caught up. But it was -6. Okay, and then it's plus 0. And I'm not even going to write the entries that I'm not going to write anymore. And then minus, again, according to the checkerboard, -6 times, and now cofactor is going to be 4, 6, -3, -5. The most important thing here is not to lose track of which column you were in. The most common error you might make. So this is 6 times -2 is -12, minus -10, so plus 10. And then plus 6 times -20, and then plus 18. And so we're going to have 6 times -2 plus 6 times -2. And so that's going to be -12 plus -12 is -24, which is not equal to 0. And the takeaway from that is that what we are talking about here is a linearly independent set. If the determinant had been 0, then that would mean the set was linearly dependent. And we can say that without even knowing any linearity relation between them. Okay. Now there are a couple other properties of determinants which are useful, and then there are a couple of sham properties that determinants don't have. And it's important to note what they don't have. So I'll do that there for a second so you can write it. But properties. Some more properties. Of determinants. Alright, and I'm just going to say these and give you a brief justification of why some of them are right. But here's one that's nice. The determinant of A transpose is equal to the determinant of the original matrix. So if you're ever talking about a matrix in which it itself is maybe not triangular in any important way, but its transpose is, then you can use that to make your life easier, and the result will be unchanged. And the reason why this is true is just think about the process of finding the inverse. So if we were to expand along, say, column 2 before, then we would get actually the exact same numbers were we to take the transpose and do row 2 instead. And the calculation would be exactly the same as what it was here. So, so the determinant of the transpose will still be the same as the determinant of the original matrix. Also, if I know that the matrix is invertible, then that means that actually the determinant of the inverse will, well, we know for one thing it's not equal to 0, but more interestingly, it's equal to 1 over the determinant of A. Now that's just an interesting fact. It is good to know. we're not going to exactly prove it here, but it is a consequence of the following also being true. If you have the determinant of a matrix multiplication where A and B are both square, so for the determinant to be defined, we have to be talking about square matrices all the way down. So not just the product is square, but actually the individual factors are square for this to be true. So the determinant of the product of matrices is then the product of the determinants of the matrices. And an extension further of that is, if we were to do a power of A, that is the same as the determinant of A raised to that power. Now, this is a consequence of this just being repeated over and over again. And if k is -1, it turns out a power of -1 is actually the same thing as the inverse, and so it's not a coincidence that they're written that way. And so these three properties are all basically coming downstream from this one. And then one more that is of some interest in other things that we will be doing later in this class is to note that the determinant of P, A, P inverse is the same as the determinant of A. And this is actually, again, a property of a consequence of the preceding properties. But what this means is, so this is what's called a similarity transformation. And if you do a similarity transformation, you do not change the determinant. So that means the determinant is what is called an invariant of the matrix. But more on that when the time is right. Now, here are some properties that determinants don't have. So these are false, fake. So they're fake properties of determinants. So if anybody tells you these are true, it is fake news. So fake properties. Fake properties of determinants. So these are tempting, but wrong. So the determinant of A plus B is not equal. So we could say fake properties of determinants. So this is not equal to the determinant of A plus the determinant of B, which means that the determinant is not a linear transformation. So that's an interesting fact. And the other consequence of not being a linear transformation is that the determinant of a scalar multiple of A is not the same thing as C times the determinant of A. There is a true version of this, though. However, the determinant of a scalar multiple of the matrix is something that we can actually figure out. So if we have a scalar multiple of an entire matrix, that's as though each row were being multiplied by that scalar. And if each row is multiplied by that scalar, then according to the properties of row operations, that means that it would be times C for the first row, times C for the second row, times C for the third row, and so on for the number of rows. So that's Cn, C to the power of n, times the determinant of A. Not that we'll make a lot of use of that, but it is a fact. So for example, then if you saw a matrix where you could pull out a factor of 2 from everything, and as a result the resulting computations would be easier, you could do so and make your life a little bit easier. Similarly, if we had ever decided that it was convenient to do so, we could actually pull a factor out of one of the rows in order to simplify our calculation a little bit, if that were ever at issue. But most of the time in this class, the determinants we're going to be taking are small enough and easy enough that it's not worth it to build up too extensive a toolkit when it comes to the properties that are useful for computation. All right, so there you go. Those are some properties of determinants. Now that answers the question of what. So section 3.1 answered the question of how do we find matrices, or find the determinants of matrices? Section 3.2 was a question of what does the determinant actually determine? Why is it called that? Well, it turns out it gives you a test for, on the one hand, invertibility, but also everything else that goes under the same umbrella as invertibility. And according to the invertible matrix theorem, that is a lot of stuff. So everything that we know from that theorem now can also be determined by the determinant. If the determinant equaled 0 in either of those previous examples, then our answer would have been the opposite of what it was. The question of a determinant is always, does it equal 0 or doesn't it? That's what's important about a determinant. And actually, that's also why invertible matrices are sometimes called non-singular, because we divide by determinants in a lot of computations, and singular here means a singularity, as in dividing by 0. So a matrix is non-singular if its determinant is not 0. Okay. Well, that'll do it for section 3.2, so I'll see you for the next episode of Math 261. Till then, bye!